video you're about to see is a real-time recording made at a live ICRI technical session. It is important for you to realize that the remarks of the speaker do not necessarily represent the views of the International Concrete Repair Institute. This presentation is intended to refresh your memory if you attended the session and to allow you to benefit from the speaker's remarks and from the question and answer period if you were unable to attend. Now here is the introduction to the speaker for this session.
Good afternoon. Our speaker this afternoon is Bill Hanley from Master Builders. He'll be talking about drying shrinkage testing of repair mortars. This is a topic that, in terms of materials, is obviously very critical. In the good old days, I think everyone, the specifiers in particular, went crazy with let's specify high compressive strength materials, and they looked at limited properties in terms of the performance of materials. I think since the good old days, we've learned from our experiences that compressive strength is not everything it's cracked up to be, no pun intended, and drying shrinkage may be one of the properties that needs to be looked at more carefully, and I think Mr. Hanley today will enlighten us on what these properties are and how there can be variations in materials regarding this property, which is an important property. Bill is a product development scientist in the Repair and Protection R&D group at Master Builders. His research interests include concrete repair materials, corrosion inhibitors, and repair material selection for corroding structures. He has a BS degree in chemical engineering from Carnegie Mellon University. It's my pleasure to introduce Bill Hanley. Thank you.
Thank you. The title of my presentation is Drying Shrinkage Testing of Repair Mortars. And the purpose of this study was to demonstrate how important it is to report the testing procedures and test methods involved when reporting a shrinkage value, because any types of parameters that you change can dramatically affect the shrinkage value itself. This is an outline of my presentation. I'm first going to begin by giving a review of the types of shrinkage that occur in repair mortars. Then I'm going to talk about the two evaluation methods that we used in this study, and then talk about the 4 parameters that we looked at in the testing program to evaluate the shrinkage methods. And finally, I'm going to compare the results and conclude. There are 5 types of shrinkage that can occur in repair mortars, the first of which is plastic shrinkage that occurs when the mortar is still soft. Next would be thermal shrinkage, which occurs, it's more appropriately called thermal contraction, and this occurs when the mortar cools down after it is warmed due to the hydration of the cement paste. The next type of shrinkage is drying shrinkage, which is due to moisture loss of the mortar. Next we have autogenous shrinkage, which is due to the inherent chemical reactions of the repair mortar, and this can cause a volume change. And finally we have carbonation shrinkage, which is due to carbon dioxide reacting with calcium hydroxide in the paste of the repair mortar. Again, drying shrinkage is a volume reduction due to the loss of water as the matrix dries. Now, water occupies volume. Therefore, when the matrix dries, you have a decrease in volume, and it results in an increase in shrinkage. And drying shrinkage will occur as long as the relative humidity is less than 100%. The 2 test methods that we looked at here, the first of which was the ASTM C157 test method, and we also looked at the ICRI modification of that test method. In the C157 method, an initial reading is taken at 1 day, and then the test specimens are immersed in saturated calcium hydroxide solution for another 28 days. Another reading is taken, and they are removed from the water and allowed to dry for another 28 days. Readings are taken at 1, 3, 7, and 21 and 28 days. The ICRI modification of that version is basically the same, with the exception that the 28 days of curing in water is removed. Here we take our initial reading at 1 day, and final readings are taken for the next 28 days in 50% relative humidity or air. Another note, if you have a rapid setting system, the initial reading is taken at 3 hours. There are 4 parameters that we investigated in this test study, the first of which was the effect of curing. And this was demonstrated by comparing the 2 test methods, the C157 and the ICRI modification of that version. Remember, the C157 has the 28 days of curing. The next, we investigated geometry effects. And to do this, we looked at 2 prism dimensions, a 1 by 1 by 10 prism and a 3 by 3 by 10 prism representing a deeper patch. Then we looked at aggregate extension. We extended each of these mortars 55% by weight with siliceous pea gravel. And finally, we varied the binder chemistry. We chose 4 different binder systems that I'll explain in the next slide. Again, to evaluate the curing effects, we compared the C157 test method with the ICRI modification of that method. We looked at 4 different binder chemistries, the first of which being a dense mortar, which had silica fume. The second of which was a polymer-modified mortar, followed by a rapid-setting cementitious mortar, which was shrinkage compensated, and finally a magnesium phosphate chemistry, which was entirely different from the other 3. And each of these 4 systems were proprietary bagged mixes. This is a plot of length change versus time for the 2 test methods. In the dark blue is the C157 length change curve. And the turquoise is the ICRI modification of that version. And I've shifted that over so that we can see how the shrinkage profiles are very similar. In 2 terms, the black arrow would represent the shrinkage that is reported by the C157 test method. However, what's more important to look at is what I'm going to call the gross shrinkage. And this is the difference between the peak of expansion of the 157 method and the lowest shrinkage that is observed. And if we overlap these 2 curves, we do see that the gross shrinkage is very similar, and the shrinkage profiles, again, track each other. The first of our results is comparing the curing effects, and here we're comparing the C157 test method with the ICRI modified version. In most cases, we see that the C157 gives a much lower shrinkage result. Especially note for the polymer modified system, where the ICRI version gives a much, much higher shrinkage result than the C157 method. The next curve, I've converted the C157 value to the gross shrinkage, which again is from the peak expansion to the bottom of the shrinkage, and we see that the shrinkage has increased in all of the values. Note that now the polymer modified system, the gross shrinkage for the ICRI and the C157 are almost identical. This is showing a plot of tensile strength versus shrinkage stress versus time. And one thing about curing is that we delay the onset of the shrinkage stress. So the dotted red line is showing a delayed shrinkage. And even though those profiles may be the same and may be the same magnitude, if we delay the onset of the shrinkage stress, we have time for the tensile strength to compensate, to increase, and we will not get cracking. The intersection of these 2 curves would represent cracking. Next, we look at the geometry effects. We compared the 1-inch prisms with the 3-inch prisms using the ICRI modified version. And in almost all cases, you could see again, the 3-inch prism shrunk much less than the 1-inch prisms. Now, for the rapid cementitious system, it was more for the 3-inch prisms, and this could be due to thermal contraction because it's rapid and you do have more heat generated. Now, some of this is cut off, but why is there more shrinkage for the 1-inch prisms than the 3-inch prisms? If we look at a factor, the surface area per volume for each of these prisms, we see that for a 1-inch prism it is 4.2 inverse inches. Likewise, for a 3-inch prism, it turns out to be 1.5 inverse inches. And the ratio of those 2 numbers turns out to be about 3. So we have 3 times more surface area per unit volume with the 1-inch prism than the 3-inch prisms. Hence, we have much more surface area for water to evaporate. we take that one step further and convert the 3-inch prism to a 3-inch deep patch with the same dimensions, again, the surface area per unit volume of a 3-inch prism is 1.5 inverse inches. That for a 3-inch deep patch is only 0.3 inverse inches, the ratio being about 4.5. Now, the surface area exposed to the atmosphere for the patch is much, much less than the prism. We see that there's only one surface exposed to the atmosphere. So again, the shrinkage bar gives the worst case scenario for these dimensions. Next, we looked again at the aggregate extension of 3-inch prisms, neat and extended 55% by weight. And in all cases, extending the repair mortar caused a decrease in shrinkage. So we can draw some conclusions about shrinkage from the results that we had with respect to the binder chemistry. For the C157 test method, the rapid cementitious system shrunk the most, followed by the dense mortar, followed by the magnesium phosphate chemistry, and the polymer modified system had the least reported shrinkage by this test method. Now if we look at the ICRI modified version, we see that the dense mortar shrunk more than the polymer modified version, followed by the rapid cementitious system, and the magnesium phosphate chemistry shrunk the least here. But if we look at the gross shrinkage of the C157 method, it is the polymer modified system that shrunk the most, followed by the dense mortar, followed by the rapid cementitious system, and the least shrinkage, the least gross shrinkage, was the magnesium phosphate chemistry. Now, why was there such a difference between the gross shrinkage and the reported shrinkage for the C157 curve? And here we see length change versus time for the C157 prisms. And during the first 28 days, you get an expansion. And note the pink curve is the polymer modified system. And we see a large amount of expansion due to the polymer swelling and absorbing water. Likewise, we see an equally large amount of shrinkage. We come back down to nearly 0. So the reported value would look very good, but the gross shrinkage is actually very high. This final curve is averaging all the shrinkage values for the different binder chemistries, and we're comparing each of the test methods tested. And across the bottom, we have the ICRI 1-inch, 3-inch, and 3-inch extended. And the next 3 bars are for the C157 test method, showing both the reported value and the gross shrinkage in the magenta. And you can see the wide variety of shrinkage results that can result, up to 80 to 90% differences based on the test method used with the exact same repair materials. Also note how well the gross shrinkage correlates with the ICRI modified version. Some conclusions we can draw. The curing effect, we saw that it could lower the gross shrinkage by up to 50%, and this was determined by comparing the gross shrinkage of the ASTM C157 method with the ICRI modified version, which did not have any curing. But more importantly, curing delays the onset of shrinkage so that the tensile strength can accommodate it. For the geometry, we saw that the 3-inch prisms had up to 89% less shrinkage than the 1-inch prisms. In aggregate extension, we saw that extending 55% by weight reduced shrinkage in all cases. And not only is using pea gravel or any type of aggregate economical, it also reduces the shrinkage because it takes up space that would normally be occupied by paste, and is the paste that shrinks, not the aggregate. Some conclusions we can make about the binder chemistry. We saw that the C157 test method was inappropriate for the polymer modified system because it expanded so much during the first 28 days. So the value we would purport would look very good because it would come back down to 0, but we see the important factor, which is the gross shrinkage, was very high. But we also saw that the polymer modified system showed the largest reduction in shrinkage when going from a 1-inch to a 3-inch patch. And in all cases, regardless of the test method and the size of the prism, the magnesium phosphate chemistry had very, very low shrinkage. So there are some recommendations that we can make based on these results. The first, the ICRI modified version gives the worst case shrinkage values. It also gives you about the same shrinkage profile that you will get with the ASTM C157, giving you the more important value, which is the gross shrinkage. So this method would be recommended for testing of repair mortars over the 157 method. We also saw that extending with pea gravel definitely reduces your shrinkage and is very beneficial to do this for deep patches because of this. Again, reporting the test method and the size of bars that were used to determine that value are very important, because just using a 1-inch to a 3-inch bar, we saw how much the shrinkage value can actually change. You should also use an appropriate test method based on the application of that repair mortar. If a repair mortar is only intended to be used for deep applications, it may be meaningless to report a 1-inch prism shrinkage value. And also, shrinkage is not the only factor when choosing a repair mortar. You should choose your repair mortar based on the application and other desired properties such as bond and modulus, rheology, and durability factors. We know that a polymer greatly increases the freestyle resistance of a repair mortar. So while we may have a high gross shrinkage in some cases, it's very beneficial for a polymer to be included. So some future work would like to investigate new test methods to evaluate different types of binder chemistries and determine which one is most appropriate for the different binder chemistries. We'd also like to relate shrinkage to cracking potential for specific materials, since it is the cracking potential that we are worried about here. We also would like to investigate new shrinkage reducing techniques and evaluate them with the new test methods that are developed. Thank you. And are there any questions? Yes?
Please review your curing method. What are the characteristics of the medium phosphate that causes you to reduce shrinkage?
This is the curing of the two test methods. The C157, you have 1 day in the forms, then 28 days in saturated calcium hydroxide solution. This is the wet curing time. You remove it from the water, and you take your final readings during the next 28 days. The ICRI modified version, you don't have that 28 days immersed in water. You simply remove them from the molds and take your final readings 28 days in air. And in fact, it's recommended to extend this to 56 days. And you can usually see your first 28 days is when you get your most shrinkage. By 56 days, the curves start to taper off. And it's the magnesium phosphate chemistry. Inherently, it's different from cement. It has an inherent chemical reaction which causes it not to shrink. It's a completely different chemistry.
Question, your one-day chemistry, when you put the test in there, you said that rapid set shrinks more than dense, more than like the phosphate and more than polymer modified, and then send that forward.
Okay. Let's go back here. Oop.
Right there. I mean, rapid set has more shrinkage than the polymer modified.
For the ICRI modified version, it did in this case. Yes, go ahead.
No, I just wanted to comment that, comparing these different types of binder chemistry, I don't think you can generalize and make a broad
you can't.
Because to me, like for example, the polymer modified under the ICRI modification didn't look as effective as the rapid set of mag phosphate. Isn't that more a function of the shrinkage system within the proprietary material?
Yes, it is.
That it might be that generalized that the polymer caused that.
It is.
Phenomenon.
It is. These are results and conclusions based on the 4 chemistries that were tested here, but not all polymer modified systems are going to shrink to this extent, and all the dense mortars may not shrink to this level. We're simply comparing the test methods here. Yes?
You seem to feel that the gross shrinkage was a better number than the net shrinkage. Could you expand on that? I don't follow that.
Well, in a patch scenario, if you moist cure, you're going to have compression of the mortar in the patch. But you're still going to have the same amount of shrinkage that is going to occur regardless if you cure, or up to 50% less. But you still have that same shrinkage profile, which is more than was reported by the C157 method. And it is that gross shrinkage that determines how likely you are for cracking to occur.
It would seem that if you're having initial expansion, that would pre-stress or compress the patch, and it wouldn't crack until you experience the net shrinkage.
Right. It does release some of the compression, but I've been told that it doesn't alleviate the entire problem, and the growth shrinkage is still what is important. Yes?
You said extend with pea gravel for
Yes.
thicker patches.
Correct.
Define thickness for a thicker patch. 2 inch thick?
It's defined by the size of the aggregate. So if you use 1/4 inch pea gravel, we're talking over 2 inches. 2 to 3 inches would be you would be able to extend. If you use coarser aggregate, then you can go much deeper even. And different repair mortars you can extend to different rates. Yes.
What was the relative humidity you tested?
It was for air. It was 50% relative humidity. Yes.
On the one slide you was showing the surface area volume ratios and the effect of that.
Yes.
You had a simulated patch, and basically you're just looking at the surface area on the top of the repair.
Correct.
Are you saying that the absorption by the substrate is negligible?
I'm sorry. Yeah. One thing I forgot to mention is that this is assuming that you have a saturated substrate condition.
Okay.
Yeah. If you do not, then obviously you will get some wicking of the moisture out of the patch. Correct. Yes.
In terms of the values of shrinkage, I mean, when specifiers look for performance, should it approximate concrete in the 350 to 400 microstrain range?
Not necessarily.
Acceptable in the 500, 600, 700 range in terms of the patch material?
Remember that concrete has coarse aggregate in it, and they usually test it in big specimens. So as we've seen, big specimens are going to shrink less, and with this coarse aggregate, that 0.05% shrinkage is very low. But if you would test that paste in a 1-inch bar, your shrinkage would be through the roof. So you have to look at other factors that are involved when choosing a repair mortar. Yes.
We use that magnesium phosphate, and it doesn't shrink at all.
Right.
Zero shrinkage.
It's very, very low.
And the other products we use, then we have to go to the extreme of curing. We almost have to babysit the patch, especially when we have these large forming pores. And it's a hot, windy day. Even when you babysit the patch, you go to the extreme. You're still vulnerable.
Right.
With some of these products, and it really doesn't matter who the manufacturer is.
Cement in its nature shrinks, and magnesium phosphate, since it's not cement, different chemistry, you don't get that shrinkage.
Yeah, that one's almost kiddie proof.
It is.
Well,
It is.
well, what about with the mag phosphates? There have been some reports that there is a high exotherm.
There is. It can. There's other problems associated with using a MagPhos system. You may not want to use it in all cases. There's different properties that you have to consider, and it does have a high exotherm. That's why you'd want to extend it to absorb some of that heat for deep patches. Any more questions? In the back? Yes.
Do you think that 28 days is an appropriate time period to measure shrinkage, or is it too short?
It is a little bit too short. Most repair mortars, you'll get a better idea of the total shrinkage at 56 days.
And your comments about tensile strength development in relationship to shrinkage, do you plan to study that further with respect to propensity for cracking?
Yes.
I would say that's more
Yes.
relevant with respect to patching materials cracking than
Right.
necessarily the shrinkage
Exactly.
element itself.
Exactly. That was part of our future work, is to study the cracking potential rather than just a shrinkage value, because you could have a shrinkage value that's high, say for a polymer modified system, but the modulus is low, correct, and your creep is high for those types of systems, so you would not crack. Okay, thank you.
Okay, thank you all. 6:30 tonight in the ballroom, and then again tomorrow morning, the theme session's here at 8:30. And if you haven't signed up yet, I don't think it's too late for the tomorrow night Chicago Feast, sponsored by the local Tri-States chapter. Thank you all. See you tomorrow.